Most AI systems already know what their actions mean. When a game engine receives action left, the programmer defined exactly what happens. When a robot receives move forward, the motion planner knows the motor commands and expected outcome. The semantics are explicit, written into the system before it runs. But ASRA-style adaptive reasoning systems work differently. They receive abstract tokens. Action 1, Action 2, Action 3. No definitions, no labels, no documentation. The system is never told what Action 1 means. All it sees is before grid, action token, after grid. From those observations alone, it must discover what each action actually does. This is action semantics inference, and it is one of the foundations of adaptive intelligence. Before we can talk about actions, we need a precise notion of state. A state is a complete snapshot of the environment at one moment in time. Consider a 3x3 grid. 0 is black, 1 is blue, 2 is red, 3 is green. One red cell sits at the center. The full grid configuration, every cell value together, is the current state. Grids use row column indexing. Y is the row, top to bottom. X is the column, left to right. Position 0, 1 is top center. In code, grid 0, 1 refers to that cell. Understanding coordinates matters because action semantics are often local. The system must identify exactly where change occurred. The before state is the environment immediately before an action is applied. Top center position 0, 1 equals 0. Black. Center position 1, 1 equals 2. Red. Nothing has happened yet. This is the baseline the system will compare against. Why does the before state matter? Because semantics inference is fundamentally comparative. The system cannot know what an action did unless it knows what the world looked like before. Without a before state, an after state is meaningless in isolation. Seeing grid 0, 1 equals 1 tells you nothing unless you also know it was 0 a moment ago. Intelligence begins with comparison. Now an action occurs. Action 1. Here is the critical point. The system does not know what action 1 means. Action 1 is only a token, a symbol, a label with no attached definition. It is not told action 1 equals increment top center. It is not told action 1 equals move left, rotate, or change color. Nothing. The action meaning is never explicitly provided. What the system has instead is a symbolic action token, known only by name, and the expectation that applying it will produce a new state. The true meaning, the latent action semantics, is hidden. The token is known. The semantics are not. This mirrors ARC environments, scientific experiments, and biological perturbation responses where mechanisms are never labeled in advance. After action 1 is applied, the grid changes. Before, top center equals 0. After, top center equals 1. Compare cell by cell. Only one cell changed. The red center cell stayed at position 1, 1. No movement occurred. No rotation. No translation. No sliding. Only a local color update. 0 to 1. Black to blue. Everything else is identical. This is a state transition. Before state. Down arrow action 1. Down arrow after state. A transition describes how the environment changes when an action is applied. The system learns by analyzing differences, environment evolution, change detection, and transition dynamics. One observation is evidence, not proof. The system localizes the change. Action 1 probably affects only top center, but it needs repeated transitions. Apply action 1 again. 0 becomes 1, 1 becomes 2, 2 becomes 3, 3 becomes 0. The pattern repeats. 0, 1, 2, 3, 0, 1. The system accumulates evidence. Uncertainty shrinks. Competing hypotheses converge. After sufficient observations, the latent semantics emerge with confidence. Action 1 equals increment color at top center. This is action semantics inference, the process of discovering what an action does by analyzing state transitions, without ever receiving an explicit definition. Repeated observations compress into a compact rule. Next at y, x equals grid at y, x plus 1, modulo 4, with only position 0, 1 affected. Grid yx is the current value in the before state, plus 1 increments the color, modulo 4 wraps the cycle, 3 plus 1 equals 4, and 4 mod 4 equals 0, green back to black. Without modulo, 3 would become 4, which is not a valid color. Modulo creates cyclic state transitions. A formula is a compressed semantic hypothesis. Instead of storing thousands of transition pairs, The system stores a rule that predicts, tests, and abstracts. The system compresses repeated transitions into reusable rules, the bridge from raw data to world models. The grid example is simple. The principle is not. The same mechanism that infers a grid transformation can infer biological intervention dynamics. In arc reasoning, action effects differ per environment. You discover them by playing, not from a manual. In decision biology, cells sense stimuli and infer hidden downstream effects from perturbation responses. In scientific experimentation, you apply an intervention and observe the outcome. The mechanism was not labeled. In every case, the loop is the same. Compare states. Detect change. Infer the operator. Repeat until semantics converge. This feeds world models, causal inference, autonomous discovery, and nature foundation models. Unified scientific intelligence built on learning what interventions actually do. In ASRA, the adaptive scientific reasoning architecture, discovered semantics feed a broader adaptive loop. Observe the environment. Generate competing hypotheses. Intervene with informative actions. Evaluate outcomes. Update the world model. Abstract reusable concepts. Repeat. Action semantics inference is not an isolated pre-processing step. It enables planning. Which action maximally reduces uncertainty? It enables world modeling. What will the environment look like after I act? It enables memory. What have we learned about this environment's hidden mechanics? It enables autonomous discovery. Systems that learn what to do by learning what actions are. Semantics discovered from interaction dynamics alone. Before you finish, try this yourself. Before grid, center cell equals 2, red. After an unknown action, center cell equals 3, green. Nothing else changed. Scan every cell. Ignore identical cells. Only center position 1,1 changed. 2 to 3. Same operator type. Increment. At a different target cell. In a real ASRA environment, more examples would reveal whether the action always targets center or varies by context. That is the next layer of semantics inference. Return to the central claim. The action meaning was never explicitly provided. The system only saw before grid, action token, after grid, repeated many times. From those observations, it inferred what actions actually do. Not from a manual, not from a label file, from state transitions. Meaning emerged from interaction. The transition from 0 to 1 at top center was not merely a color change. It was evidence. Understanding state transitions is the beginning of understanding intelligence itself. This is the foundation of ASRA, adaptive reasoning systems, world models, scientific intelligence, and autonomous discovery. Learning the semantics of intervention through state transitions.